I'm Adam Simmons, and here with me again is Chul from Analytic Folk, and we're in round two talking about machine learning. Appreciate you joining us, Chul. And from last time, you got into a lot about your background, education, how you transitioned into the machine learning field. You were you were working with particle physics before, I believe that was what it was.
Right.
So you came from an interesting background transitioning to machine learning, and over the years, you've become an expert in it and understanding, the ins and outs on different methodologies, and you helped us get a quick background. We'll call it a crash course into some of the terminology and where someone might get started from an educational standpoint. So I kind of wanted to start off there, and then we can kind of dive into some of the deeper topics with machine learning. So to kind of go back on the education standpoint, what areas, what schools do you think are the best for machine learning right now? If someone were to approach of looking for a school to get them some started.
Honestly, right now, I've always liked the Coursera courses. I mean,
So your option. So your advice to somebody is you don't have to necessarily go to somewhere with formal education. Go towards something that's freely available or available online and open.
Well, so it really depends on what you're doing. I mean, if you go to like the Stanfords or the Carnegie Mellons of the world, then you're going to get incredible, like in-depth understanding. You'll probably do the calculations in order to see how all of it was working or whatnot. But honestly, you don't really need that level of depth in order to get started with a lot of this stuff. Honestly, there's, as I think I said this in the last cast as well, that there's so many libraries out there, and there's so many like tutorials, there's example notebooks and things like that. So there's lots of material already out there if you just kind of want to start kicking the tires and getting an intuition. Because along with the in-depth understanding of it, it's really important to kind of like just start playing with it in order to develop those intuitions. I think those really go a long way as well as a formal education. So,
and just to remind our listeners, you one of the resources you mentioned last time, besides Coursera, was a website called Fast.ai, and
right.
I had to and I checked that out in between our sessions. And it's incredible. It's actually written in a way that even for someone like myself doesn't have any real developer experience or technical help. I'm actually kind of grasping what they're talking about, what they're getting at from the different abstracts or different topics. They give some good approaches and examples of how machine learning is used. So it's a great website, great resource. And this time around, we're going to make sure that's posted in our episode notes for everybody to look at.
Yeah.
And can you tell us a little bit more about the resources on that website and what's helped you out build a foundation for what you're doing now?
Sure. No, I mean, the thing about Fast AI and Jeremy Howard, essentially he's kind of, he says this, the approach he takes is the one that I've been saying as well. And it really is, you have to you don't need to, do 4 years in undergraduate, you get your PhD and all this to mess around with it. And I mean, if you decide to go that route, it is much slower and it's not necessarily more effective, because a lot of the intuitions that people developed are just doing it by hand rather than, just trying to do calculations on pen and paper and whatnot. And so the nice thing about this website is also they've released a library as well that makes it easy. So if you want to train up your own classifier, say, if you want to train up something that'll tell the difference between dogs and cats or whatnot, he has a library that will let you, download your images, it'll ingest it, it'll put it in the proper format for use with a library called PyTorch, which is one of the more popular frameworks that people use nowadays for deep learning.
So with that said, you mentioned the resources that he has available. Can you point us in the direction of some other resources folks can take advantage of, maybe open source training data, just to kind of get some other foundation behind data to use when just playing around?
Yeah, there's lots of training sets available. It also depends on what you're trying to do. And so there's a couple, as far as computer vision goes, there's a couple there's a couple popular data sets, and they also have there's specific reasons for using each one. And so, it really boils down to, there's a couple. So I'll start by kind of explaining some of the different types of problems that people face with computer vision, and then I'll go into some of the data sets that people are using. So
great.
A lot of times when people, there's a big question between something called classification versus object detection. And so when people talk about classification, essentially, imagine you take an image and the image has a cat in it. You essentially want to say, this image has a cat in it. You don't really care where it's at. You don't care what its position is or whatnot. You just say, this image has a cat, or this image has, a car in it. So the other problem that I've spent more of my time on is something called object detection, which is not only do you say that this image has a cat in it, but you actually put a bounding box around it and say, here's the cat, that, here's where the cat is in the picture. And a step further beyond that, something called segmentation, where instead of just putting a bounding box, you actually put a pixel level mask around the cat and say, this is where my cat is. And so there's three different, computer vision is much larger than this, but when it comes to trying to identify things, these are typically the three of the more popular ways that people actually try to look at stuff. And so for each of these tasks, there's kind of data sets that are better and worse for doing what you want to do. I mean, classification started off with the ImageNet data set, and so that was several million images. There was also there was some level of annotations for doing object detection as well, for that localization and object detection. Some of the other popular ones that people use is Microsoft released the common objects with common objects. It's called the MS COCO dataset, COCO. I think it's common objects in context or something. Forgive me if I'm messing that part up. But that one would allow you to, have it has the bounding box information as well, it has segmentation information. So if you wanted to do those type of problems, there's a really huge data set that came out more recently than ImageNet and COCO, which is called Open Images. I forget how large it actually is, but at some point you probably need terabytes of storage in order to stash some of these away. And so those are some of the more common ones. When you're getting started, there are smaller data sets that you can mess with. The CFAR 10 is like 32 by 32 like pictures, and there's several of them. There's 10 class categories, and so at that point you can kind of if you have a toy model you kind of want to play with first, maybe start with those. If you actually want to start building out more serious capabilities, then you might go with some of the bigger data sets and whatnot.
Great. No, thank you for pointing those resources out based off of what you're trying to do. So on that note, at what point does someone decide, hey, I'm going to build this stuff on my own computer, and where would someone pivot and start doing this within a cloud, for example? How demanding from a resource standpoint is machine learning on your own computer?
So I would say even for some of the smaller projects, at some point you probably need a GPU to do this.
GPU is as simple as getting a nice NVIDIA graphics card or something like that, right? I got a 2070 in my computer right now. So. Right.
And so, yeah, it's at some point, if you probably want a good, at least 6 to 8 gigabytes on your video card, right? The ones I play with are usually the 1080 Ti's are gone now, the 2080 Ti, but those have 11 gigabytes. And then, as you start to move to the cloud, you get access to the V100s and things like that. And there's also the Google Cloud has their TPUs that you can run serious things. But I guess to go back to answer your question, a lot of times, if you're essentially, so there's a process that lots of people use, which is called transfer learning, or you can also, it's called transfer learning, or else you can also sometimes refer to it as fine-tuning a model. Slightly different, but effectively what happens is that these really massive neural nets that people have trained from scratch, taking like millions of images and whatnot. What you can do is, if the objects that you're looking for are kind of similar to the ones that are publicly available in these data sets like MS Coco or Open Images, what you can actually do is you can take their models and then just slightly tweak them with significantly less data that you have, on the order of hundreds or thousands of images, and still get a reasonably performing system. So stuff like that, a single GPU at home, you're fine. If you actually have a new architecture that you're testing with, and you have millions of images that you're training against and whatnot, at that point, you really kind of have to parallelize this out and spit it out across multiple GPUs in order to get it to train in a reasonable amount of time.
And in your perspective, what cloud environment would you choose, just to kind of say, hey, they have the most resources that I can take advantage of? I know a lot of folks like defaulting to the Amazon cloud, but I want to kind of give a perspective of what else is out there and why that might be a good choice.
Sure. I mean, Google is actually developing a lot of stuff specifically for their TPUs. They have examples for tensor processing course. And so, I mean, they have obviously a solid environment as well. I mean, Azure also has this, so it really boils down to which one you're most comfortable with. I mean, I think there are advantages to each one, but I mean, for the most part, at the end of the day, you get several GPUs. You have to somehow figure out how to get the training parallelized and whatnot across them all. And so, I mean, I wouldn't necessarily recommend one or the other. I would just say it's whatever you're most comfortable with.
No, good to know, and that's good advice. So with that, getting spun up on machine learning is one thing. Understanding how it works is one thing, but trying to decide where to focus of what project you're working on can be a challenge for a lot of folks. And that's where there's a lot of websites out there offering challenges or examples of how to use machine learning. And one of those that has gotten popular over the last year or two, especially when it comes down to computer vision or satellite or area-based machine learning, is spacenet.ai. You're familiar with this website, correct?
Yeah.
Can you tell us a little bit more about it? Whether you've worked with a challenge or not, I'm sure you've actually looked at it and kind of taken a peek and have some opinions, right?
I feel bad because I mean, I was thinking of when you mentioned SpaceNet before, I was thinking of XView, and so the XView challenge, I was a little more familiar with.
Go ahead and talk about XView first.
Okay. So I mean, the XView challenge, there was another one released, I think late last year, but the one that was released, I think the year before, 2 years before that or so, it's essentially it's a data set that was put out by DIUX. And essentially what it did is, I think they had 60 different categories.
And just to reiterate, DIUX is the Defense Innovation Unit Experiment
Yes.
at the National Geospatial Intelligence Agency.
Right. And so what they did is they released, a bunch of, essentially, I believe it was 30 or 50 centimeter satellite data. And they had gone through and labeled, you have the statistics in front of you. And so, 60 different classes, 10 million objects. And,
well, hold on just a second.
Mm-hmm.
There we go. Screen updated. So I'm looking at the XView page right now.
Okay.
So you can see that by the numbers.
Yeah. And so this is a good data set to get started with if you're working with satellite imagery. I mean, there are definitely some issues with it. I mean, there's massive data skew and things like that. So you have to do some tricks in order to get things to train properly. But I mean, as far as a big annotated data set of satellite imagery, this is usually a good one to start with for object detection.
Looks like they focused a lot more on disaster response as well with this.
That was for the second XView challenge. So what the second XView challenge did was it actually had a bunch of before and after shots, and then segmentations of various things of interest like buildings and whatnot, I believe. And so this is really.
And I'm going to read this directly from the website so that folks who are just listening to the show and not watching it on YouTube, the website, from a disaster response, applying computer vision to overhead imagery has the potential to detect emerging natural disasters, improve response quantify the direct and indirect impact, and save lives. So it comes down to when we're trying to assess a disaster area, the damage overall, we collect images very, very quickly using overhead imagery, whether it be aerial or satellite. And can a computer process this imagery in near real time to a point where we can detect things like helicopters or helicopter landing pads or different equipment available that might indicate the specific status of an area, or if emergency responders can go in there and use the resources available to either perform rescue or help build up an area, or help allocate an area towards disaster response and rescue operations. So there's a lot of aspects to that, including figure out where the damage areas are too, just from a computer standpoint, rather than trying to use maybe hundreds, if not thousands of people to understand what's going on, or send people into a dangerous area and assess the damage as the disaster is going on. So there's a lot of benefits to this, and trying to get a machine to do this. So I guess that's what you said the second challenge was all about.
Yeah, and so what it does is it has a lot of it. What's cool about it is it actually has before and after pictures of the same area that they've geo-registered, and then they have essentially various things in the before images kind of segmented out. Like I think it was buildings, and there are a few other classes, I believe. And so, but the DIUX has really been interesting, or the XView data has really been interesting for like object detection, and now trying to do segmentation against the mass that they've provided for the Hatter work.
So actually, even in this paragraph right here, a couple of the things you've already mentioned, right? So the XView follows in the footsteps of challenges such as common objects in context, or COCO, and seeks to build off a SpaceNet and functional map of the world to apply computer vision to the growing amount of available imagery from space. Yeah. So this builds off of existing stuff that you've already mentioned, including TensorFlow, Object Detection API, and PyTorch. And actually, I don't think you mentioned TensorFlow before. Can you explain that real quick?
Sure. So each of them have each major company has kind of the platform that they've created or invested time into and money. And so TensorFlow is actually Google's deep learning framework. And so TensorFlow 2.0 came out last year, but before that, particularly when you're talking about the TensorFlow Object Detection API, that's still TensorFlow version 1, since there are some issues in trying to migrate it to TensorFlow 2. But what it is, it's actually, and I've used actually TensorFlow and PyTorch, the detection models for. I'll get into PyTorch afterwards, but TensorFlow Object Detection API, and essentially there's a few dozen different pre-trained models that you can start with, and so it gets pre-trained weights that have been trained against MS COCO and other data sets. Then you can kind of use those you can either use those out of the box, or you can also use those to fine-tune against your data sets to do that. So PyTorch is released by Facebook, and so the reason I think people like PyTorch a little bit better is when it came out and whatnot, there's a lot more flexibility, as far as control. I mean, when I work with PyTorch, it's like, you're kind of working straight with Python and whatnot. TensorFlow 1, essentially, but I don't want to go into too many specifics about why it was, but essentially you would have to make function calls in order to make things run. There was something called a session that you had to start, and everything had to kind of run through the session. As you start to work with it, I mean, it actually made a lot of sense. I mean, particularly for deployability issues, I actually did prefer TensorFlow 1, the way that you could save off the graph and just run it without having to have additional code wrapped around it. Something that unfortunately, with PyTorch, you have to have the model definition along with the weights. And so it's definitely pros and cons to each one. Another one is MXNet, which is the one that AWS or Amazon put their energy behind. It's an Apache project, Apache MXNet. And so a lot of their examples, even though even though all three of the commercial vendors will support, each of them, they typically have preferences, and when you see the various tutorials or whatnot, they'll kind of focus on the ones that they've developed. So Microsoft also has one called CNTK, but I think they're spending more. I think Microsoft is spending more of their time trying to do like Onyx and get behind some of the other ones as well that have a little more momentum.
Awesome. No, thank you for that. I think once again, the more terminology we discuss, more we get into detail, I think that helps. I think once again, we have a habit of when we're involved in the industry so long, just roll out these terms and not realize like, oh wait, this is a common term for me, but I might actually have to explain this a little bit more.
Sure. Okay.
So Space.ai, back to that. So it's a lot like EIUX XView. But this one is sponsored. Well, this one's provided by Space.ai. They offer a challenge, and they're about to hit their 6th challenge.
Right.
And that challenge is going to be wrapped around freely available Capella radar imagery.
Oh, nice.
And they so they're trying to do. Let's see if I can find this a little bit.
So sorry to go back to SpaceNet. Now that I have my bearings straight, I mean, when it originally came out, there was several. I think it was a terabyte or 1.2 terabytes or something, and essentially it was building masks, and so it had a bunch of building footprints. I think they updated it to have the road network as well, and so now you can actually try to model roads. But that one was kind of designed more kind of towards the segmentation problem of how do I get the footprints out for various buildings and whatnot over geospatial data. So,
well, I think this challenge, the 6th challenge, is something similar. So the training data set contains both SAR and EO imagery. However, the testing and scoring data sets contain only SAR data. So the problem is, consequently, the EO data can be used for pre-processing the SAR data in some fashion, such as colorization, domain adaptation, or image translation, but cannot be used directly to map buildings. The data set is structured to mimic real-world scenarios where historical EO data may be available, but concurrent EO collection with SAR is often not possible due to inconsistent orbits of the sensors, cloud cover that will render the EO data unusable. So that's part of the problem there. So they what can they do to extract what is there when typically EO is available, but when it's not for various reasons, what can SAR see that overlaps with the EO imagery? So the data over 120 square kilometers of both high resolution synthetic aperture radar data and electrical optical imagery with 48,000 building footprints labels for Rotterdam, the Netherlands. So it's a huge data set for folks to play around with. Now, the data set for this challenge has been released in the last week. However, the challenge itself, I don't believe doesn't start until mid next month.
Okay.
So with that said, from your opinion, how long does it take typically to grab some data like this, start playing around with it, and figure out, can I figure this out? Is a month enough time for the challenge? Is that what's your opinion on that?
Yeah, and so as you've taught me, SAR is definitely a different beast than working with EO data, and so the EO data is typically a bit more straightforward. I mean, most of the things that are currently trained are against RGB, the 3-channel RGB.
For the sake of our audience, I've asked a lot of questions in this show. I've asked Chul a lot of questions.
Right.
But to give a little background, I'm a geospatial analyst by trade, and I used to do a lot. Well, I guess I still do nowadays. Do a lot of radar exploitation, so I know what I'm looking at when I look at a radar image. So that's what Chul's mentioning when I've taught him a lot about radar image.
Yeah, definitely. And so, I mean, the pixel values themselves even are completely different with SAR, and so you have to do the appropriate scaling and contrast and whatnot. But assuming that you can pre-process the image to where you get a normal typical looking grayscale image, I mean, a lot of times just to kind of test out these things, it's relatively straightforward to take a pre-existing model out of the box and see how it performs. I mean, usually that doesn't take too much time. A lot of times the big hurdle is getting the data into the format that the PyTorches or TensorFlows or MXNets of the world want them in. And not only the images themselves, but the annotations that have been provided. There's a particular format that each one will want to put in when you start messing with it. So, once you're comfortable with doing that, getting the data in the correct format, and with the annotations in the correct format, usually it's pretty straightforward to just test out to see how it's going to do. To try to do some simple things, simple fine tunings to see, hey, can I get it to slightly improve or whatnot. And then after you start doing things like that and test out a couple different architectures, then you can say, okay, is there something else I really have to try in order to get these things to work? So a lot of times when you read what people have done, it's, sometimes they're remarkable, sometimes they're simple, but a lot of times, even the simple ones, they'll have tried 50 different simple ones, and they hit the one that actually makes a difference. And so even when something kind of looks like, that looks straightforward, the amount of time it takes to get to that conclusion oftentimes can take a while. So
if someone's interested in participating in this challenge, have never messed with SAR imagery before as a machine learning, somebody who's working on machine learning problems, what would the advice you'd give them to say something to think about or consider?
I tell them to find someone like you, honestly. But,
and that was not a leading question. I wasn't expecting that,
but honestly, when I first saw it, the SAR particularly, the first thing is when you open it up, if you try to open it up straight, it looks black. And when something happens like that, one of the first things I'll do is I'll actually take the pixel values themselves and throw them in a histogram and see how they're distributed. And so if you do that with the SAR imagery, you can tell really quickly, yes, it's a very nonlinear distribution, a really long tail, and a huge spike near zero. And so, some of the simple tricks I was applying was just, apply some nonlinear. Essentially take the log of each of the pixels or something simple like that, and then just try to mess with it from there. And so, but there's a handful of different tricks. Actually, if you look through Kaggle, if you're looking for data sets, Kaggle is actually another place that's actually pretty cool.
That's a new reference. Talk to me about Kaggle and what it is and why it matters.
Kaggle, I believe they're bought out by Google, but essentially, people post challenges there all the time. It's not necessarily, there are some geospatial challenges, but it's just all over the place. They'll put challenges up for anything and everything. And so what you can do is a lot of times there are data sets. What's cool, what's even cooler about Kaggle though is along with the data sets themselves, they actually have people who post notebooks saying, hey, here's how you would pre-process this, or here's how you would, here's how you would get rid of this type of noise or that. I believe there's one of the things I was looking through was for SAR imagery, they're like, here's how you despeckle SAR. And so they have some hints. One of the challenges I was messing with a while back was, MRIs, which are these DICOM images. And, it's wonderful because you'll have these people just posting notebooks about, hey, if you get these DICOM images, here's how you process them, and here's how you make them look like normal pictures. And so this is actually a really good place where you can kind of go and find information and whatnot. And also, the people who win these challenges, usually they have pretty interesting solutions that they'll post. They'll post code, they'll post write-ups and things like that.
So if you were to summarize what Kaggle is, it's would you call it a library of resources to include data sets, notebooks, or a collaborative space for machine learning projects overall?
Yeah, I don't know if I'd say collaborative. There's a collaborative component to it, but I think there are limitations to what the notebooks can do. And so, not surprisingly, because if you try to train something serious against it, it gets expensive. So, a lot of the times people will take it onto their own machines and work on it. But what this is it's really a bunch of competitions that various people can, you can join the competition, you can try things out, but the nice thing is the collaborative side of it is that people will just post. Hey, here's some of some initial exploratory data analysis that I've done on this data set, and they'll show you statistics here's the distribution of the classes, and Here are the various.
So here's a couple of the numbers. Use over 19,000 public data sets and 200,000 public notebooks on Kaggle. That's quite a bit. And they're not just about, once again, computer vision problems. This is machine learning in general. Yes. So, for example, I even see a tag here, look for financial data sets and then there's tons of different categories in here.
Yeah.
So many that you have to search for it. Education, leisure, arts and entertainment. I mean, literally it's tons of stuff.
Yeah. So this is probably also, if you're like just getting started and you're like, I just want something to work and I just kind of want to try something out, then honestly, you might want to consider just going to search for a Kaggle challenge to see if someone had done something similar and see what they've done.
Micro challenges, solve ultra short challenges to build and test your own skill. So that's pretty good. That's so if you're wondering what you can do and where to get started, this is an excellent resource.
Mm-hmm.
Awesome. Well, appreciate that, getting into that. So I want to get into one more topic before we sign off. And thank you for this second round with machine learning. Quickly, I wanted to discuss so Forbes.com released an article recently related to the top machine learning trends for 2020. And I'm just going to focus on the computer vision trends. And I wanted to get your opinions on this. The first being 3D is currently one of the leading research areas in computer vision. What do you think about that?
Google recently released their. I think it's a whole package that will do the 3D. But the one that there might have been, my apologies if there are ones that are earlier than this, but the Mesh RCNN is one of the ones that I remember seeing. And what it really is trying to do is it tries to take a 2D scene and essentially make a voxel instead of just reproducing pixel mass. Is actually 2D pixel mass is actually try to give you like voxelized information back about the 3D space that it's and reconstructing these 3D areas. It's definitely pretty neat. It's not something I've personally focused on, but the ability to do this is certainly pretty fascinating. And it's one of those things that the things that people can come up that you can do with these neural nets is more and more impressive and whatnot. So it's definitely an interesting direction. Kind of curious to see how it develops in the next few years.
Okay, so the second trend on Forbes.com is for computer vision is the popularity of unsupervised learning method is growing. Why is unsupervised learning methods growing faster than other methods?
Well, so the reason is because the bottleneck for a lot of the technologies, a lot of the approaches, even the ones I was talking about, require lots of labeled data. And so, which is called supervised learning. So what you literally have to do is, if you want, to find a bunch of bicycles in pictures, you have to go through a bunch of images, use various annotators or whatnot in order to kind of annotate, yes, here's where the bicycle is. You feed that through, and then, you can get it to find bicycles. And so unsupervised it's always been popular. They're just trying to come up with more novel ways of using it nowadays. And what that is essentially, instead of labeling the data, you just say, here's a big bucket of data. Please tell me what's in it. And so, from that perspective, you're no longer limited by, the amount of label data that you have. And oftentimes, if you're looking for something completely novel that, that isn't like something that, has been in one of these public data sets that people are looking at, then a lot of times you do need a lot of labeled data to get things to work. And so as these unsupervised techniques come out where, I don't need the labeled data, here's just my big bucket of data, and I want to find X, Y, and Z. That's why it's always been popular, and it's one of those things that they'll continue to try to develop.
Okay. The last trend from Forbes.com for computer vision research. Computer vision research is being successfully combined with natural language processing to better image caption retrieval and visual grounding. Can you tell us what that means?
Yeah, and so a lot of times you get additional metadata you get additional information, right? So this is about trying to capture as much information as possible. So along with the picture, if you actually have text as well describing it, or vice versa, then you can you can better identify things, right? Sometimes if you see reports and you see an image, and your system is designed to find cars, and so it finds cars, and then you have additional data like some news feed that says, oh, in this location there was like a van walked by, or a van drove by. Then you can take that information as well and say, oh, this must be a van. You can start to do correlations and things like that. And
so is this form of correlation it could also be looked as a different form of assisted machine learning, with the NLP assisting the computer vision algorithm on how to kind of narrow the results?
Definitely. But I think what this is really boiling down to when they're talking about it is that when you're working with images, and it's just, especially when you're trying to classify things, and also with the natural language processing, what you're ultimately doing is you're converting the image, the 2D pixel space with however many channels you're dealing with. You're constructing like essentially a mathematical vector. So, and what you can do with the language as well, with the words and whatnot, is you can actually also make a vector out of those. And then what you can start to do once you actually convert those into vectors is you try to see, you try to train something that's going to learn both of these vector spaces at the same time. So you can kind of start to go back and forth between them. And so part of it is, yes, it's the language kind of helping out, but it's also, here's additional information. I've turned it into this mathematical thing that can now be trained, where I can now train them together. And so doing stuff like that is kind of a lot of what this research is trying to do.
Awesome. No, I appreciate it. There's a number of other trends on the Forbes.com website. We'll link that in our show notes as well. But for as far as computer vision, that's it. And I think that's going to wrap up our machine learning round 2. And I want to appreciate you, Chul, for coming back again and discussing this.
Sure.
Next time, we'll prepare a little bit ahead of time, maybe show some actual examples of imagery, object detection or something with what's freely available out there, just so folks can actually see what's going on. But with that said, if you enjoy listening to the show, we ask that you support us as we continue to provide great content on the geospatial industry, discussing news, best practices, having guest speakers related to the latest industry projects. You can contribute to our continued operation through anchor.fm/projectgeo/support or patreon.com/projectgeospatial. Your contribution keeps our website running and funds our ability to cover conferences on various events beyond the GeoInt Symposium. If you represent a company in the industry and would like to talk about your product or service on the show, please reach out to us. Appreciate you listening. And once again, this episode is going to be on YouTube, but it's also going to be distributed through audio on anchor.fm. So thanks, everybody. And once again, thank you for Chul for participating.
No worries. Have a good day.